Okay, now that we have a general way to write a polynomial for any function, let's look at one you already know. Let's look at sin x. We already worked with that one, but I just showed you what it was, but let's look at why that's true. So we're looking for a third degree polynomial. What we're looking for then is we want it to be, I'm going to put approximately a third degree polynomial, because just a third degree polynomial will not match sin x everywhere, as we've seen. So this is going to be an approximate, and we want this to be written in the form, whoops, third degree. So this will be d plus cx plus bx squared plus ax cubed. That's what we're looking for. So what we need to know then, in order to find a, b, c, and d, we need to know some derivatives. We need to know, first of all, what f of 0 is equal to. We need to know what f prime of 0 is, f double prime, and the third derivative. All right, so f of 0 is the same thing as the sine of 0, and the sine of 0 is 0. F prime of 0, so the derivative of sine is cosine. Cosine of 0 is 1. Derivative of cosine, negative sine, that's still 0. And the derivative of negative sine is negative cosine. That's negative 1. Right, if we put this into the pattern we found for any Maclaurin polynomial, we would say that f of x, or sin x, is approximately this third degree polynomial. And we're going to take f of 0, that's 0, plus f prime of 0, which is 1 over 1 factorial, times x to the first, plus f double prime of 0 over 2 factorial, x squared, plus the third derivative over 3 factorial, x cubed. And I hope now you can start to see the pattern. This is what we found before, or what we saw before, is that sin x only has odd exponents. That's because the first derivative of sine, the derivative of sine is 0, so that original term goes away. And then when we get to the second derivative, that's also sine, and at 0, sine is equal to 0 there. So all of those even-powered terms disappear because the even derivative comes back to sine again, and sine is 0. So this is where we end up. That's why sine is the way it is. If I would have asked you to find a fifth degree polynomial, you would just continue to do that. So that's why sine works out the way it does. So if you can't ever remember, like, oh, which one was sine? Was it that the odd powers, or was it the even powers? You can always just build it again by finding the original, the first derivative, second derivative, third derivative, and put it into that Maclaurin polynomial pattern. Okay, now let's try one that we haven't seen yet. Find the third degree Maclaurin polynomial for e to the x. I'm going to give you a chance to go try that. So pause this, go try. Okay, welcome back. So we need a third degree. I'm going to actually make a fifth degree because it'll be easier to see the pattern. And I know you did a third degree and it's fine, but I'm going to make this a fifth degree polynomial. So the fifth degree polynomial, we have f of x is approximately this fifth degree polynomial. And the fifth degree polynomial, I'm going to have to work from the back because I'm not sure what letter. Ax to the fifth, bx to the fourth, cx cubed, dx squared, ex, and f. All right, we know that we're going to need derivatives here. So we know f of 0 is e to the 0 power. Anything to the 0 power is 1. The first derivative of e to the x is e to the x. So e to the 0 again is 1. So the second derivative of e to the x is e to the x, e to the 0 is 1. I think you see the pattern. This is going to happen over and over again. So in order to write this function, to find a, b, c, d, and so on, we know that f is the result of f to the 0 power. Oops. We know that's just plugging 0 into the function. We know that e is the first derivative over 1 factorial. We know d is the second derivative over 2 factorial. So let's start plugging some of those things in. We know that f of 0 is 1. F prime of 0 is also 1. And 1 again. I'm going to write this 5th degree. That x to the 5th is not supposed to be in the denominator. So the way we typically write at e to the x is like this. Because all of the numerators are just 1, we usually put the x up above. So we say 1 plus, since 1 over 1 factorial is 1, that's 1 plus x squared over 2 factorial, x cubed over 3 factorial. All right, so you're seeing the pattern, I think. Oops. Especially if I write it correctly. What I'd like you to do now is write the general polynomial for e to the x. I want you to say, what is the polynomial for the entire polynomial for e to the x, to infinity? So go take a moment, see if you can write that out. Okay, e to the x is this infinite polynomial, which is 1 plus x. Just write a couple of these specific examples, and then dot, dot, dot out to the general term, which is x to the n over n factorial, and then dot, dot, dot. And we talked about before, how good of a fit is this polynomial to sine x? So let's look at how good of a fit is the Maclaurin polynomial, is this polynomial you just wrote. How good of a fix is this for e to the x? So go graph a few terms of this polynomial we just wrote. How good of a fit, what is the domain of convergence for this polynomial to e to the x? Let's go find out. So I'll graph e to the x. I hope you're using your calculator and not Desmos. So there's e to the x, and now let's write 1 plus x. Not a very good fit. Let's do another x squared divided by 2 factorial. I bet that's just over here, maybe? There it is, 2 factorial. Not bad. That parabola is pretty close. Let's see if we can write more terms. Plus x cubed divided by, divided by 3 factorial. That's starting to be pretty good, but only for a small domain so far. So let's see if we can add more terms. I'm not going to waste your time by typing all of this in here, but I will tell you that the more terms you get, the better this fit is going to be, because this curve is going to start to flatten out, and it's going to start to look pretty good. So I want you to just determine, based off of this, what I would say is that it looks like we might have an interval of convergence for this 4th degree polynomial. -1 looks pretty good. I'm going to say -1 on this left side. Now let's go look at the other side. I can go a little past +1, I think, on this one. It looks like a pretty good fit up until about 1.25 or so. 1.1. So I would say the interval of convergence for this fourth degree is -1 to positive 1.1. You could talk me into 1.2, but 1.1 feels pretty good. Add more terms to this and see what happens to the interval of convergence. And we'll talk more about it later.